Hello, folks. My name is Pedro Varela, and I'm here to walk you through solving the house prices prediction challenge from Kaggle using TensorFlow decision forests. I use Giztema's Jupyter notebook as the foundation for my solution, and you can find the link to this notebook in the description below. I hope you enjoy this tutorial, so let's dive right into it. To begin with, we need to import our essential dependencies, which include TensorFlow, TensorFlow decision forests, and 3 key libraries: Pandas, Seaborn, and Matplotlib. We'll use these to handle and visualize data, as well as conduct some feature engineering. Next, we'll load our training dataset, which can be found in the specified file path. We'll create a pandas data frame named dataset by reading the CSV file. With that done, we can take a look at the head of the training dataset. It contains both numerical and non-numerical features, such as lot area, year sold, and sale condition, all of which play a significant role in determining the sale price. We can also observe some null values, which we'll address later. Our label, or the target variable, is the sale price column. Notice that the ID column is redundant since the pandas data frame already includes an id column of its own. Therefore, we can drop it. We can inspect the types of feature columns using the info function. It's evident that we have a mix of int64, float64 and object types, along with some columns with very few non-null values. Turning our attention to the label, let's describe its numerical characteristics. We'll find the mean, median, and other statistics, indicating that the majority of house prices fall between, say, $12,000 and $20,000. To better visualize the density distribution of prices, let's create a distplet. I want it to be displayed in blue, with 100 bins. From the distplet, we can see that the majority of house prices lie between $12,000 and $20,000. Now, let's examine how the numerical features are distributed. As per the column information, these features are of type int64 and float64. To get a better look at them, let's create a data frame containing only these features. Within these features, we find the label sales price, which we should drop. Now, we'll plot the distribution. Given that we have 36 features and the label sales price, it's better to create smaller histograms. This dataset consists of a mix of numeric, categorical, and missing features. Luckily, according to Giztema, TFDF TensorFlow Decision Forests supports all these feature types natively, requiring no preprocessing. This is one of the advantages of tree-based models, making them an excellent entry point to TensorFlow and machine learning. Next, we'll split the dataset into 2 subsets: a training set and a test set. We can achieve this using a function that employs a test ratio, set to 30% by default. It generates an array of random values between 0 and 1, compares each value with the test ratio, and creates a Boolean mask to indicate which elements belong to the test set. The function then returns the training set containing data points not selected for the test set and the test set containing data points chosen for evaluation. As a result, we have 1019 examples in the training set and 441 examples in the test set. Now, we need to convert the dataset from the pandas format into the TensorFlow datasets format. We'll specify the task type as regression, since that's what we're going to do. By default, the task would be classification. Moving on, we'll use the default configuration of the learning algorithm to create the random forest model. A random forest is a collection of decision trees, each trained independently on a random subset of the training dataset. This algorithm is unique in that it is robust to overfitting and easy to use. We'll compile the model using the mean squared error metric. Finally, let's train the model. The model is now trained, and we can select a tree to display below. Let's select the tree of index 0, and let's visualize it with a depth of 3. Before training the dataset, we manually separated 30% of it for validation, which we named valid.ds. We can also use the out-of-bag score, or OOB, to validate our random forest model. To train a random forest model, the algorithm chooses a set of random samples from the training set, and the rest of the samples are used to fine-tune the model. The subset of data that is not chosen is known as out-of-bag data. The OOB score is computed on this data. The training logs show the root mean squared error evaluated on the OOB dataset according to the number of trees in the model. Let's plot this. Now, let's run an evaluation using the validation dataset. The high MSE is normal because we are looking at the squared error, and the label is non-normalized. Finally, we'll predict the competition test data using the model. We do this through rf.predict in the test data frame, creating a new data frame called output that holds the ids and the predictions. To submit the results in a CSV format, it's better to use the sample submission as a template. With the help of pandas, we'll transform our submission data frame into a CSV file. This example had a Kaggle score of 0.14860. For this competition, the smaller the better, because they are accounting for error, not accuracy. And there you have it, folks. Thank you for watching this tutorial.